will show up.
That's the plan. Well, thank you very much. Thank you to the organizers for the invitation. It's a great privilege to be here. I'm speaking on some joint work with Saharan, and when I first submitted the idea for the talk, the proof seemed very, very hard. And as I prepared for the talk, the proof got easier. So I probably have more time than I need, which gives me the opportunity to speak to you first about the Mary Ellen Rudin Award. I would like to take this opportunity to advertise. So we have the Mary Ellen Rudin Young Researcher Award. We're just ready now to start taking applications for the coming year. It's a very nice award. It's for anybody who publishes in topology or set theory. The criteria are, would Mary Ellen Rudin have been interested in your work? That's kind of the criteria. And you should be no more than 3 years beyond your PhD, so please get out the word. I do. It's on me. It's on. Yeah. Okay. So, no more than 3 years beyond your PhD. Just let me mention that the sponsors of this award are Elsevier Publishing and 3 conferences so far. We would like to add to that: the Spring Topology Conference, the Summer Topology Conference, and this conference. This year's winner, I did invite her to this conference. Katie Mann is this year's winner. She graduated from Berkeley just last year. She works more in geometric topology, and she was eager to come, but unfortunately she was busy moving to Brown, so she got a brand new tenure-track job at Brown. So that just shows you the level of participants in the award. Okay, so if anybody, if you know, letting people know about applying, just tell them to get in touch with me. I was going to add one more thing, that Ishvan is on the advisory board, Saharan is on the advisory board, Stable is on the selection committee, so we're certainly well prepared and eager to receive applications that are more set theoretic. All right, so I'm going to talk about this new name I've given to an old concept, and I'll spend the first part of the talk, well, here I actually have an outline. So I sat down and thought of an outline and then realized I probably wasn't following it. But so many of the results I'll mention throughout are joint with Saharan. And so I'm going to tell you very soon what is an almost Clopin set. And it actually has a very nice set theoretic description as well as a topological description. I'm going to begin by telling you probably the most interesting part of it, how this notion has actually appeared in many instances of being a very useful concept in studying N-star and applications. And I'm going to define what I call a simple almost Clopin set. And a simple almost Clopin set will have a cardinal invariant kappa attached to it. And the current work involves, because I was noting that all instances of almost Clopin sets that had appeared till then had always been what I'll call symmetric. Right? I'll say what that means. And so today's result is that they can be asymmetric. So I'll have some existence and non-existence results about almost Clopin sets. And then at the end, some open questions, but I'm not saying necessarily the concept is really, really interesting, but you can generate lots of good open questions in a very easy way. So here's what an almost Clopin set is. It's analogous to a cut point in continua, but it will be working in N-star, for example. So you can say that a subset A of a space X is almost Clopin. It only makes sense. No, okay, makes sense. Why is it? Okay, let me just continue my thought. So it's called almost Clopin, right? It's when you calculate the boundary of A, which is simply A will be closed, and A intersect the closure of its complement, and what we want is that to be a single point. So it's almost Clopin. It's Clopin except for one one point. And we need to say that the point is also a limit point of A, because I don't want to talk about a singleton point would be a single boundary, but okay. So, so this is the picture that I've come to draw. So here's the closed set A, and there's its boundary point. And then when you take the complement of A, there you have X minus A, which strictly speaking doesn't have this point in it, but when you close that, it does have this point in it. And a few years ago, I spoke to Saharan about some questions like this, and he named these tie points for the obvious reason. It looks like a bow tie, right? So a bow tie. Half of it. Well, yeah, no. This picture was a tie. This is a tie point, and now I'm just focusing on the left half. That's right. So I've basically said this. So if A is almost clopin, take away the point, the boundary point. Now you have an open set, and if you call it B is the other half, X minus A union the boundary point. So it turns out that it's also almost clopin, right? So the complement, so to speak, of A is also almost clopin, and we'll indeed call it the almost clopin complement of A. So change that to B. And in previous papers, we use this notation. The space X can be written sort of as this direct sum of A and B that overlap at the point X sub A. And these used to be called tie points. But as I said, now I'm focusing on the structure of A rather than the point itself.
Basically, isn't it the same as the butterfly?
No, butterfly point, these sets are simply closed, but they don't union up to the whole space, right?
Oh, that's right.
Yeah.
I think the substance.
Yeah. Right. All right, so here's the set theoretic translation, which I'm sure many of you prefer. So, of course, if you have a point in n star refers to the stone check remainder of the discrete space n, and the points of beta n are usually represented as free ultrafilters on n. And now you have this almost clopin set A, and remember that if you remove the point X sub A, that's open, and open subsets of n star correspond to ideals, so you can form the ideal of all infinite subsets of n whose remainder are subsets of A. So you get this ideal. And then similarly, the complement of A is also almost clopin, and it turns out if you do that to the complement of A, you get the orthogonal ideal of I sub A. So you get all infinite subsets of n that are almost disjoint from every member of I sub A. So that's what these tie points look like set theoretically. So you have the maximal dual ideal to X sub A, and it can be partitioned into two and give you the right notation for the ideal generated by the union of these two ideals. So that's what it is set theoretically. And as I said, let me look at some of the history to justify why I think looking at these things is worth it. So way back in 1960, Fine and Gilman. So in the early days, the study of beta n was all about continuous real-valued functions. Gilman and Jarrison wrote their Rings of Continuous Function book. And so if A, so they didn't call it this, but if A is an almost clopin subset of n star, then if you remove the point, the boundary point X sub A from n star, so that point's gone, then this subspace, this dense subspace of n star is not C star embedded, which means the not C star embedded means there's a continuous real valued function on the complement, which can't be extended to the whole space. And as I said, the study of beta n, beta x at the time was all about which real valued functions extend or not. Well, it's pretty obvious why this is true. The function which is constantly 0 on A minus X sub A, and the function which is constantly 1 on B minus X sub A is a continuous function on the subspace that won't extend to the whole space. And they also noted that if X sub A has character aleph 1, they were working in CH at the time mostly. If X sub A has character aleph 1, then each of A and B will be copies of n star. Now, I'm highlighting this because this is an ongoing theme where it's very important when you find your arbitrary subspace of n star, we really want to know, is that a copy of n star? Is it homeomorphic to n star? And these guys will be. If x sub a has character L1, those will be copies of n star. And then later, Nancy Warren, who was a student of Mary Ellen Rudin, she proved that such subspaces are not normal. So when you kick out a point out of n star, the resulting subspace is not a normal topology. So that's historically how they first arose. If x in n star has character LF1, then it will be the boundary point of some almost Clopin set. So under CH, every point is the boundary of some almost Clopin set. On the other hand, remember we just saw that if you kick out x sub a, you have a dense subspace which is not C star embedded. On the other hand, 80-something Jan. Eric van Douwen, Ken Kunin, and Jan van Mil proved that it was consistent that if you remove a single point out of n star, the resulting dense subspace is always C star embedded. So in particular, therefore, no point is the boundary of an almost Clopin set. So there's no almost Clopin sets. Baumgartner's name is there because Baumgartner showed that the proper forcing axiom satisfied this was Kunin's gap stuff, where Kunin proved there was only a certain limited number of gaps. No. So another application was, so if you kick out a p point of character LF1, then it is a boundary of an almost Clopin set, so A and B. And remember, Fine and Gilman proved that each of them were homeomorphic to n star. And so now they're homeomorphic to each other. And so you get that point, x sub A, can be the unique fixed point of a self-automorphism of n star. You send A over to B. Now you can think of it as a propeller instead of a bow tie. You can spin the propeller halfway around, and you've got a homeomorphism of n star. And then such a homeomorphism can't be trivial, because Froelich, I think, proved that the fixed points of homeomorphism on a extremely disconnected space always is Clopin. And if it was a trivial homeomorphism, that means it extends to beta n, and then so you would have to have a Clopin set of fixed points. So here's another common theme, building autohomeomorphisms of n star that are not trivial. It is, of course, has a great history. So now I want to say what I call a symmetric almost Clopin set. So an almost Clopin set will said to be symmetric if you can do the propeller. So if A is homeomorphic to B by a homeomorphism that is the identity on the common point. So that propeller goes around, halfway around, A over to B, B over to A, and it's the identity on the common point, and that, the same way I just mentioned, gives rise to these non-trivial autohomeomorphisms. That was symmetric. Now here's simple. So A is said to be simple of type kappa. Very simple to say in the ideal sense. So the ideal I sub A, it has a cofinal increasing chain of order type kappa. So that's nice. So you just go into the ideal and you're able to find this increasing chain. And the Fine and Gilman almost Clopin sets were simple of type Aleph 1. And the remark generally is that most of the appearances I'll be mentioning of almost Clopin sets to date have been symmetric and simple. And the next instance is a great result of Boban. So Boban proved that the proper forcing axiom, you start with the proper forcing axiom, and then you build a Aleph 2 distributive proper poset and force with it. And what does he do? Well, he didn't think of it this way, of course, but you add a symmetric, simple, almost Clopin set of type Aleph 2. That's literally what the forcing builds. So it builds an A and a B, and A and B are homeomorphic to each other by the automorphism that's the identity at the common fixed point and what he was after. was that the L of 2 distributive says you preserve Martin's axiom, so you get a model of Martin's axiom. And so this is the first model of Martin's axiom in which there were non-trivial autohomeomorphisms, which is not true under PFA famously, and also Boban under OCA. So that PFA says all autohomeomorphisms of n star are trivial, and this was proving that that's independent of Martin's axiom. So that was the next really interesting case in which almost Klopin sets arose. And then the post set that Boban used, you could call it of type Veličković because you can modify it, you can make changes to it. And a paper of Saharan and Juris Steprans studied it, and they proved that actually, I think, not type Veličković, but literally Veličković, that post set in that model. So although there is a non-trivial autohomeomorphism, they proved in that model, you preserve enough of PFA that autohomomorphisms in that model are somewhere trivial. And then actually Juris, on a paper of his own, that there are Klopin sets on which, if you restrict the map to that Klopin set, it's induced by a map on the integers. Yeah. And then Juris went further, and he looked at products of Boban's post set, and he was able to produce a model where the number of autohomeomorphisms was strictly between C and 2 to the C, which was a brand new idea. Now, I wanted to say that, so again, with the theme that we really do like to know when you're looking at a space that sort of looks like n star, is it actually n star? And most of the time when we are able to prove that it's not, it's because of Saharan's result about no non-trivial automorphisms. And the specific post set used by Boban, I haven't been able to, and I don't know that anybody else tried. I wasn't able to show that the almost Klopin sets that Boban adds are not homeomorphic to n star. I can't decide, but I wanted to know, and I'll get to that in a minute. But there are modifications of this post set which can do a number of things. So you know, by modifying the post set, I was able to get almost Klopin sets that neither one of them was a copy of n star, but also they weren't homeomorphic to each other, so I lost the propeller action. I can get almost Klopin sets that one of them is a copy of n star, and its almost complement is not, so that's not symmetric. I also was interested in preserving a model where there were still no non-trivial automorphisms, and anyway, I'm just mentioning some history, some more investigation into almost Klopin sets. Not especially interesting, but this was what got me interested in almost Klopin sets originally. Eric van Douwen produced a remarkable countable space and no isolated points, and its stone-check compactification, he proved, was a 2-to-1, this was a countable space, its stone-check compactification was a 2-to-1 image of n star, which is very bizarre. So every point in the image, the pre-image, was at most 2 points. So n star is hugely non-separable, and yet it mapped continuously by a 2-to-1 map onto this separable space. And then a friend of Eric's, Ronnie Levy, asked the question, what if you make the map precisely 2-to-1? So every point in the image has a precise 2-to-1 pre-image. What can you say? And he conjectured that the image, a precise 2-to-1 image of n star should always be a copy of n star, and he had some partial results on that. And my student worked on this. And so under CH, it's true. Every 2-to-1 image of n star is a copy of n star. That's because under CH, anything that remotely looks like n star is a copy of n star. And under PFA, it's also true, but for a completely different reason, because under PFA, there's no non-trivial 2-to-1 maps from n star. So the only way you can get a 2-to-1 image of n star under PFA is you take a Klopin set, you take its complement, and you map them together. So that's a trivial 2-to-1 image of n star, which is obviously a copy of n star. But in the analysis In the CH, we were able to get non-trivial maps. In this analysis, almost Clopin sets naturally arose. From the structure of the 2-to-1 map, if it was non-trivial, these almost Clopin sets would naturally arise. And so still working on the question, the consistency of 2-to-1 images not being a copy of N star, we were able to solve it with Saharan. So we could take Boban's post set. Actually, we looked at the square. The square of Boban's post set gave us two versions, almost Clopin set 1 from the first coordinate post set, almost Clopin set 2 from the second coordinate post set. And this quotient space, this was the hard thing to prove, this quotient space, which looks a lot like N star, I mean, this is 1/2 of one of these tie points, this is 1/2 of a different tie point, and all we did was we identify the two boundary points. So under CH, that is a copy of N star. The two different guys, we glue them together. Right. So why does that do any good? So this was not a copy of N star. That's where all the work was. This idea arose in my students' work. So you just take the free union of two copies of N star. That is a copy of N star. And now I'll tell you the 2-to-1 map. You just flip B1 over onto A1. So every point except the boundary point will have precisely two pre-images. You flip B2 over onto A2. Now we're getting to this. Every point except the boundary point has precisely 2-to-1 images and pre-images, and then you glue the 2 points together, and now every point has precisely 2-to-1. So the quotient of this space by deleting that guy and deleting that guy and gluing the 2 boundary points together is that space, and it wasn't a copy of N star. So it's independent whether or not 2-to-1 images. But there's the Clopin sets. It was a tool. Okay, and the final and probably the best application, well, maybe not the best. Boban's yours was great. Piotr Koschmider has gotten interested in almost Clopin sets, and because he sees it arising in Banach spaces. So you take a Banach space. What is a complemented subspace of a Banach space? Well, it's if there's a bounded linear projection from the Banach space onto the subspace, and the kernel of that projection is the complement. And so that's what a complemented subspace of a Banach space is. The continuous functions on N star is a very important Banach space. It's L infinity mod C0. And so there was a 1991 paper where it was proven under the continuum hypothesis that this Banach space is primary. What does primary mean? If you have a complemented subspace of that Banach space, then either it or its complement is a copy of C of N star. That's a lot like finding copies of N star. So that was a question raised in the paper I'm about to show you, and they proved that the continuum hypothesis says that it's primary. What's great about this question, the question being, is C of N star primary, is that's the only thing that's known. Under the continuum hypothesis, it is primary. I don't think there's any other result that tells you any other model, any other thing. Okay. So far, no connection to almost Clopin sets. That's coming. In the earlier paper where the problem was posed, it was proven that if you have an almost Clopin set, or actually, in fact, any retract, the almost Clopin set is a retract of the space because you simply map the entire complement onto that boundary point, and that's a continuous map onto the almost Clopin set. And then it follows, because of it's a retract, that the continuous functions on that almost Clopin set is isomorphic in a very obvious way, isomorphic to a complemented subspace of C of N star. So what's great about this is it's a way of finding complemented subspaces of C of N star. It seems to me the obstruction to solving this question is the inability to find any interesting complemented subspaces of C of N star. So with this idea of almost Clopin, there's a little overlap. The C of A and C of B both have the continuous functions at X sub A, but in this paper, some results show that you can merge those and get rid of them. So anyway, so C of A is isomorphic to a complemented subset of N star, and C of B is its complement. So there we are, and there's Piotr's question in the open problems 3, I think. Is it consistent to have complementary almost clopin subsets A and B so that neither of these guys is a copy of C of N star? Because then you've solved the question of is it primary. So there's my final historical remark about how almost clopin subsets have been interesting and still may be. Okay, that's just some remarks. So, I mean, this is an appealing conjecture because I already said, I'm no expert. I have tried working on this. I don't know much about Banach spaces, but I do say that from what I've seen, and I asked Piotr, there's no nice complemented subspaces of C of N star to look at, but this gives you a couple. Okay. So now I'm going to just talk about almost clopin sets without applications. And so we have seen the construction of simple, meaning simple of type kappa. The ideal has a cofinal chain. Symmetric, almost clopin sets. And so I've been interested in just seeing if, just because it seemed an obvious question, what kind of asymmetry can we get? And my prototype question, and I asked Saharan a couple of times, was this one, whether you could get complementary almost clopin sets that were both simple, but one of differing types. So cofinality Aleph 1, cofinality Aleph 2. And I shouldn't speak for him, but he seemed to think that was feasible. He thought he could do it. And so now other asymmetry measures you might investigate are just obvious local cardinal invariants of the point x of A in A. Or cofinality, what sort of cofinal subsets of I sub A are there? What sort of cofinal subsets of I sub B are there? All those sorts of things. Another one that I'll probably forget to mention later, so I'll do it now. I've also, in an earlier paper, said, okay, if you've got a tie point so you have an almost clopin set A and it's got its complement, can you have that? You might call that a 2-point. Can you have a 2-point that can't be written as a 3-point? Don't know. Or a 4-point. Lots of questions. So here's some tools to analyze almost clopin sets. There's a couple of definitions. So let's say you have a subset of N star. It's known as strongly discrete if you can find an almost disjoint family of infinite subsets of omega of N so that A beta is an element of X beta. Topologically, that's the same as surrounding the points of the discrete set by pairwise disjoint neighborhoods. So that's strongly discrete. An important notion in the study of topological spaces are free sequences, uncountable free sequences. It's just simply that the closure of the initial segment of the sequence is disjoint from the closure of the final segment of the sequence. Maybe I'll leave it at that and won't read it out. And then such a sequence, and they have a beautiful paper about if you have free sequences, could you have them that actually converge? So can you get your free sequence X sub beta less than lambda to converge to the point, meaning every neighborhood of the point contains a tail of the sequence? So those are some notions. And I'm going to generalize this converge. Let's say that a family of infinite subsets of N converges to the ultrafilter X if the corresponding family of clopin subsets converge. So that's a way to say that. Is that if you take any member of the ultrafilter, a tail of the A gammas are all mod finite contained in that member of the ultrafilter. So you got this point, and these clopin sets get, in metric spaces it's trivial. If you have a sequence that converges to a point, you can surround the members of the sequence by smaller and smaller epsilon balls, and they converge to the point as well. So that's what it means to say that a family converges to our ultrafilter. So this is a tool to analyze almost clopin sets. So let's think about an almost clopin set and its witnessing, a simple one, and its witnessing sequence A alpha alpha less than kappa. If you just look at the successive symmetric differences, A alpha plus 1 minus A alpha, which we'll assume is always infinite, that sequence, in this sense, converges. And so that's a strong thing. This sequence of infinite sets converges to the limiting ultrafilter. It's also a local pi base at that ultrafilter. It's a familiar notion. A B scale, Soft called them. So F sub C will just fix in advance, not change, will be a B scale, a mod finite unbounded family consisting of strictly increasing functions. And here's I think Bloss might have used this notation, just sort of the indexing function of an infinite set. The next member of the set A above the integer k is a useful function. Okay, some more tools to analyze almost clopin sets. We'll say that an infinite subset of n reaps a family. That word and notion is due to von Douwen, I think. Y reaps a family A if Y splits every member of A into two infinite pieces. So A intersect Y is infinite and A minus Y is infinite. And the reaping number R is known as the least cardinality of a family that cannot be reaped, which, beautiful result, Balsark and Simon, corresponds to the least pi character of a point in n star. So that's that notion. And I want to refer to a result from Goldstern and Shalaw's paper where they proved that R, the reaping number, can be less than U, the ultrafilter, minimum cardinality of a base for an ultrafilter. And in that paper, they use this. So if a family cannot be reaped, then the indexing function is an unbounded family. It's not hard to prove, but it's useful. I came up with this word. Now I was thinking about this. Say that a family A is hereditarily unreapable if every subset of it with the same cardinality can't be reaped. And just made some observations about this. If A is a converging sequence, converging to an ultrafilter, it's certainly hereditarily unreapable. If the splitting number is the continuum, then there is a hereditarily unreapable family. You can just inductively build one. In the Mathias model of the splitting number being the continuum, there is no converging family, but there is a hereditarily unreapable family. I wasn't able to my satisfaction, decide everything in this model. It's a very interesting model. So there is no converging family, but I couldn't determine. So there is a unreapable family of size aleph 1. That's what that means. But I couldn't work out whether or not there could be a hereditarily unreapable one. Doesn't matter. I was just making observations. And if you had a bunch of Cohen reals, then there's no hereditarily unreapable family. So just putting those notions on the table. All right, so we're going to analyze almost clopin sets. So definition, I want to make a connection to simple p kappa points. They've been in the news. A point is said to be a simple p kappa point, and I'll just say it this way to show the connection to almost clopin sets. If the dual ideal has an increasing cofinal chain of type kappa, it's the same thing as saying the point has a type kappa well-ordered filter base, mod finite, ordered mod finite. And we'll say a point is an almost p kappa point, or one might choose some other name. Found an old paper where it talked about almost p spaces. So anyway, if you take fewer than kappa many members of the filter, of the ultrafilter, fewer than kappa, that will have a pseudo intersection, which need not be in the p point case. That pseudo intersection would be in the p point, and here we're just saying it has a pseudo intersection. All right. Well, why do I introduce all these things? Because if you have a simple almost clopin set, then that point is an almost p kappa point. It's just trivial, but it's just going to be useful as we discuss further. Well, because if you take fewer than kappa many neighborhoods of the point or members of the ultrafilter, you just go high enough in your cofinal thing to get inside them all because of the converging. So it's just a fact, okay? So simple almost clopin is an almost p kappa point. And finally, let's completely standard If you have an ultrafilter on N, you have the functions from N to N, order them, mod the ultrafilter, and that gives you a linear order, and I'll just use the letter eta sub x to denote the cofinality of that ultrafilter ordering. Okay, so here's finally something new. Everything was old until now. So here's the theorems. All right? So it answered the question I said was my prototype. So if A is almost Clopin, and if both it and its complement are simple, then they have the same type. So you cannot have aleph 1 converging from the left, aleph 2 converging from the right. If they're both simple, if they both have a cofinal sequence, the cofinality is the same. And this is the reason why. So if let's look at kappa. So if this cofinality along the ultrafilter is bounded by kappa, then kappa will be D. Kappa will be the dominating number D. If, on the other hand, kappa is less than the cofinality, then kappa will be B. So it's either B or D and no other choices. But since they both have to, A and its complement will both have the same ultrafilter, it's either one or the other. It's either both sides are B or both sides are D, and there's no other choices. So that's the first theorem. And then the second theorem is to get the best asymmetry. Well, I don't know about the best, but here is some asymmetry. So if kappa and lambda are regular cardinals, and lambda needs to be bigger than or equal to the continuum for this to work, then there is a CCC poset that will force a simple, almost Clopin set of type kappa. So that'll be the A. So A will be simple of type kappa, and kappa is arbitrary regular cardinal. And in the other side, right, so we can't make it simple and make it asymmetric. But what we can do is we can get a free lambda sequence. That's why I gave you those definitions. So a free lambda sequence from the other side. So in some sense, the cofinality on the other side is as big as you want it to be. So that's the new ultrafilter gun, that we can get the asymmetry. All right. So how much time is there? 10 minutes. Which is plenty, but I just try and decide how much you might want to see of the proofs. So that's the end of the results. So here is why if the cofinality along the ultrafilter power is below the type of the kappa, the type of the set A, ideal I sub A, then kappa must be D. So here's just an easy checking lemma, so I won't bother with they're not gory details, but they're just technical details. If you have a family A that converges to your ultrafilter X, and you take this original B scale, and if that B scale is unbounded in the ultrafilter ordering, then you just run through the converging family A and just look at this family of maps. F sub C from the scale, and the next member, sort of the enumerating function of that member of the converging family, then that turns into a dominating family. It's very simple. Every function is bounded above by one of the F sub C's by some member of the ultrafilter. One of these members of the family A that converges to the ultrafilter will be inside, and then you look at this and you get that this function is bigger than the one you started with. And that means that if you have a family that converges to an ultrafilter, that the cardinality of that family must be at least D. And on the other hand, if you do have a family that converges to an ultrafilter, then it can't be more than D. So it's bounded above by D. So a converging family converging to an ultrafilter is bounded above by D, and if the cofinality was less than the cardinality of your family, then it's above D. And this is simply because of Goldstern-Shaw result that if A converges, it's hereditarily unreapable, So every size, full-size subfamily is therefore this family is unbounded, and therefore if D was less than the size of the family, and every one of these functions is bounded above by somebody in the dominating family, and the pigeonhole principle would tell you that this goes wrong. So that's it. That's why if eta sub x is less than or equal to kappa, then kappa is D. On the other hand, if kappa is less than eta sub x, so then that family B sub c, c less than, so I do need to point out that kappa is certainly at least B. So kappa converges to this ultrafilter. It is hereditarily unreapable, so by Goldstern's law, it has cardinality. Kappa is at least B. But if B is less than the cofinality, then that, as I said, F sub c, c less than B will be bounded above modulo the ultrafilter. But whenever that happens, that resulting point, any ultrafilter where the cofinality is bigger than B, is not an almost B plus point. And you may remember that for an almost Clopin set, it was an almost P kappa point. And so that says that kappa is bounded above by B. So it's very simple. So that's it. That's why there can't be two types. And then I won't go into a lot of detail about how we force an asymmetric Clopin set. So we start at the top. We just force a lambda increasing chain that's probably going to be dense. So there goes these B sub x's, I said beta less than lambda. So this is this increasing mod finite chain, and as I said, if you just force one, it's probably going to be dense in the space. And we'll start trivially, A sub 0 is probably going to be the empty set, but let's just imagine here's A sub 0 almost disjoint from every one of these B's. So these B's are going to be sitting in the ideal I sub B, and we're going to build I sub A by an iterated forcing. And at step delta, before we get to kappa, we will inductively, I should have said a little bit more here. So I've got this increasing chain, B beta beta less than lambda, and it'll have a boundary. So this will have a boundary. Simply the union of the B beta stars, take the closure. There's a big boundary there, and we'll start the induction, and we'll pick a point at stage 0 of the construction sub A. So that'll be our approximation to the boundary point of when Saharan was explaining this to me, I said, I don't see how we can pick the ultrafilter because you can't preserve ultrafilters and so on. He says, oh, no, don't worry. We keep it secret until the end, which ultrafilter is going to be X sub A. So then the first step of the forcing is we simply diagonalize with standard sigma-centered forcing. We add a pseudo-intersection to this ultrafilter we picked at step 1, and we bring it over here, and that pseudo-intersection is A1 minus A0. So A1 minus A0 is a pseudo-intersection to X sub A, and then A1, and we just move it over to the side for our picture, and so there's our A1. And so, and then, now what was X superscript 0 sub A that is now in the extension simply a filter. It even has pseudo-intersection. It's probably got huge pseudo-intersection. So it's a great big closed set now. And at this next stage, after choosing our A1, we go inside that huge closed set and we choose a new approximation, X1A. So extending that filter, and now it's an ultrafilter in the extension. And we always maintain that it's always on the boundary of these B sub betas, beta less than lambda. And then, so that's it, except at limit steps. At limit steps, we've been building this increasing chain. And so now you basically have a gap here, this increasing mod finite chain of A deltas. We've been building this shrinking family of ultrafilters. And what we have to do is we have to mod finite separate the left-hand side from the right-hand side. The bizarre thing is in this construction, it seems like these A's are just so far away from the ultrafilter that how on earth is this converging? But the genericity takes care. So we just simply split the gap. The A beta is beta less than, or A alpha, alpha less than delta, but we split it from absolutely, so these inductively are always orthogonal to the B betas, but look what we split. So we split A alpha, alpha less than delta from its total orthogonal complement. So every set, not just the B's, but every set that was almost disjoint from each of the A's, that's a huge ideal. and we mod finite separate A delta will mod finite contain this, and be almost disjoint from everybody there. So that's what A delta looks like. And then we extend this ultrafilter, then we diagonalize, and then we continue. This forcing is simply Heckler forcing at countable limit stages. But at cofinality, if delta had cofinality omega 1, this is a big problem. It probably isn't CCC. In fact, if you don't take care, it's not. But anyway, that's the induction. So we just simply keep diagonalizing the ultrafilter, take the pseudo-intersection, put it over there, put it at, it's really a new ring, and keep going. And at the end, the union of these filters, in model delta, this was an ultrafilter, and so in the final model, the union of those filters is an ultrafilter. So there's the ultrafilter, that's the boundary point, and the only hard part about, not really hard, but about the argument is to prove that these A alphas that we've been building along, that they actually converge to that ultrafilter, and that's not that hard to do. And we always kept on the boundary of the B betas, and so this point we ended up with X beta is, the XA is on the boundary. And originally the argument used a measurable cardinal for lambda and then factoring the poset in a million different ways, well, lambda many ways. But actually just topologically removed all that. You can just prove that because lambda ends up equaling C, and this point is on the boundary of this increasing chain of Clopin sets, you can just prove topologically that you can pick a point, and get it to you can diagonalize the ultrafilter and get it to converge. And so that's where we get the free lambda sequence converging to the boundary point. So that's easy when kappa equals aleph 1. That's the proof. And when kappa is bigger than aleph 1, that darn thing is certainly not CCC. In fact, you prove it's not CCC. And so you have to make some changes, not very many, it turned out. Instead of separating it from its complete complement, you only separate it from, at cofinality omega stages, you only separate it from the union, increasing chain of complements is in the earlier models. And then you force, and by doing that sort of more generically at stage delta, it allows you to prove that at uncountable cofinality stages, the splitting forcing is still CCC. And that's it. Oh, yeah, questions. So here we'll just finish with some questions. So can there exist simple, almost Clopin sets of different types? I proved that you couldn't have them, the same guy witness two different types. But we don't have a model where you have an almost Clopin set of type aleph 1 and a different almost Clopin set of type aleph 2. And that's probably difficult, and it's probably related to what you're doing on, so the big, Heike's working on simple P aleph 1 points and simple P aleph 2 points. And so this is really a version of that. In fact, if you have a simple almost Clopin set of type kappa, I wonder if you necessarily then have somewhere else a simple P kappa point, right? So does the existence of these convergence in this sense imply somewhere else in N star there's actually a simple P kappa point? Because they certainly look similar.
What are the characters of the things that you construct?
This guy has character lambda. Yeah, lambda. This, yeah, C, right. So, yeah. Is a simple almost Clopin set of type aleph 1 a copy of N star? This is a different question in disguise. So we're always interested in, do you get copies of N star? But if you look at this question preceding it, if there is a simple p point of character aleph 1, then yes, every such thing by Fine and Gilman is a copy of N star. So this is equivalent for aleph 1 only, not for bigger cardinals. It's really saying if you have a simple almost Clopin set of type aleph 1, do you have a p point of character aleph 1? Or even a point of character aleph 1, I think. No, p point. And Martin is working on that, right? So that your paper would answer this question, I think. Does the complement of a simple almost Clopin set, so this guy, now you look in this big monster B, it's very complicated. Will inside there, will you get, so sitting inside of B, an almost Clopin set of the same type as this guy? It won't be a different type because of the previous results. They didn't have to really be complementary to not be able to exist. It was enough that they converged. I just wonder about that. And I guess that's it. That's all I have. Okay. Thank you.